Okay, here's a little video about section 2.6. We're talking about maybe the first new thing, linear regression. As opposed to correlation, regression is the act of actually making a line. Correlation is the act of looking and seeing how linear things are. So we've got two things, and this is the second of the two. So here's that same example that I showed in the video about using the calculator. We've got chirps per minute along the input axis, the independent axis, the explanatory variable. We've also got the response variable, which is the temperature, the dependent axis. So we can make a regression line that fits this data as good as possible. We're going to talk more specifically about what that means to fit the data as good as possible is, but for now, let's just think about the generic equation of a line. Any line has a slope and an intercept, and that's all it needs. This is y equals, we call this the slope, even though it's the letter B, we call this the intercept, even though in this case it's the letter A. This is y hat, because y hat isn't the actual explanatory variable. Y hat is the predicted value of the explanatory variable. If I plug, of the response variable. If I plug an explanatory variable in here, I get a predicted value for the response variable here. You can stop this and check this out as much as you want. It's a rehash of the video I did. Here I should have used the letter zero, or the number 0, I used the letter O. Oopsie. Notice here, chirps are in Y2, chirps per minute are in list 2, temperature is in list 1. So you want the explanatory variable to be chirps per minute. You have to do this. If you plug in the temperature as the explanatory variable, it'll give you a regression line, but these numbers won't be measured in temperature. These numbers will be measured in chirps per minute. And this slope will not be measured in temperature per chirps per minute. It will be measured in chirps per minute per degree temperature change. Correlation has the same R regardless of which variable is the input and which variable is the output. Of course, if you're trying to fit a line, it makes a difference whether the intercept is measured in degrees or whether the intercept is measured in chirps per minute. So as you could well imagine, it's pretty easy. All you have to do is plug in 140 chirps per minute right here, and that gives you a predicted value for the temperature. In this case, it's almost 70 degrees. Here's what it looks like from a graphical standpoint. If the chirps per minute are about 140, we predict that the temperature would be very close to 70 degrees. There's the algebra. So, give yourself a little quiz. If the crickets are chirping 180 times per minute, it seems like the only possible response would be 80 degrees. A little bit below 80 degrees, it looks like. Interesting question is, how far is the predicted temperature from the observed temperature? What's the difference? In this case, when there are 103 chirps per minute, the predicted temperature is 61.39 degrees, pretty exact. The observed temperature for 103 chirps per minute measurement was 63.5. So there is a difference between what was predicted and what's observed. If we take what's observed and subtract what's predicted, we can see that there's a difference of 2.11 degrees. We call that difference the residual. That's the residual for that input. The observed value, the predicted response value, one is called y and the other is called y hat.